So we're going to have two parts of the lecture in the last topic. All right, you can get back to what you haven't finished with task 3. So now let's focus back on the slides on the projector on your screen. Now we're going to talk about geometric property and geometric distance measurement. So it may be a surprise to you that for the spatial data, we actually don't have some geometric property embedded in the data. So as we know, you guys listen up. As we know, in the vector data is defined by points for the point feature and the vertices for the polyline and polygon features, right? But we don't really have the properties such as the area or perimeter. But these properties are very important in many spatial analysis. So we want to measure or calculate the area parameters of these shapes. So in ArcGIS, we can easily do that with a measurement tool or calculate these geometric properties using the attribute table. So these are very simple, but I want you to understand how the distance or area are calculated in different coordinate systems and on different data models, namely the raster and vector data. So if we were working with a projected coordinate system, so very straightforward, the distance between 2 points are the straight line. And the line is calculated based on the two coordinate, the coordinate of these 2 points. Okay? And then in the geographical system, coordinate system, as we mentioned in the very first class lecture in this unit, it's not a straight line, but a arc segment of the great circle. So this distance here is calculated using this equation based on the latitude and longitude of the points on the spherical coordinate system. And now the measurement of length is also different with raster and vector data. So you can imagine it's very simple if we want to get the length of a polyline. It's basically the sum of the lengths for different line segments. And in vector data, it's calculated based on the number of cells and the cell resolution. So if it's a straight line, vertical line, then we can just get the length by multiplying the number of cells and the cell resolution, right? So each cell is 50 meters in this case. And if it's a oblique line or inclined line, so we're going to use the diagonal distance of that cell. So now the cell's length becomes the square root 2 multiplied by the cell resolution. So in this case, that's 50 multiplied by 1.414. This is also useful later on. We'll talk about calculating the shortest path. And it's also using diagonal length before moving to a cell that is diagonal to the existing cell. Now for measuring the perimeter and area, it's also different in vector and raster data. So in vector data, for perimeter is very easy. Basically, again, the sum of all these line segments. And the area is calculated by summing the areas of the trapezoid. So if we have a line segment here, then we basically go to vertical lines to the x-axis and calculate the area of this trapezoid. And now if we sum all these trapezoids together, we see this trapezoid here is a negative value because xi plus 1 minus xi is a negative value in this case. So eventually we'll get just exactly this area here using this equation. Okay? So again, you're not required to calculate this, but understanding how the area and parameter are calculated in different data models are very important. And with raster data, as you can imagine, it's much easier to calculate the volume, the area, but it's a bit trickier to calculate the perimeter. So again, we're using the cell resolution, so we know the length of each cell. And the perimeter equals to the total number of cells multiplied by 4, so that's all the size, right? Minus the shared cell size in the area. So in this case, the total number of cells are 21, and the shared size are 30. So for example, this is 1 shared side, 2, 3, 4, 5, 6, 7, 8, 9. So that's 30 in total. So that's how the perimeter of a raster data is calculated. Now remember the very first JS lecture, you were asked to use the buffer tool. And at that time, you may not have a good understanding what buffer is for. Well, now we're going to revisit the buffer tool and understand how we use it to create or analyze our data. So the buffer is a distance measurement tool for only vector data. And it creates a zone around the feature or set of features with a distance or width specified by the user. If we look at a point feature, the buffer is created around it and represented by a circle, right? Because that's an equal distance from that point. So what if we have a set of point features? Let's say they are the cellular network towers. We want to see whether these towers can cover this entire area. There's no gap between the coverage. So we can create a buffer with the distance of the range for the signal and examine whether it can cover the whole area. Or it could be a buffer for a line feature. So imagine the line is a road network, and we're concerned about the impact of noise from the road. So we want to see what's the area will be affected by the noise. Or it can be a river. We want to set a protective area along the riparian area along the river. And in some cases, we want to assign different buffer, different width for the buffer. So imagine this could be a road network where we have the highway and the local road network. And again, we're concerned about the noise level. Then with highway, the speed limit is higher, and we also have all these big trucks. So the noise impact area may be bigger than the local roads. Okay, so we can assign variable distance for different features. So when we create a buffer for different features, they may have overlap. So we can use the dissolve to combine different buffer areas to get a single coherent buffer zone. Because later on, when we use the buffer shape for overlay analysis, it can be easier for the processing. So you'll see how the dissolved shape is for different feature types, for points, lines, and polygons. in most cases, you'll be working with the data set from a small area. Could be a city or a neighborhood. But think about it, when we deal with data set from a very large scale, for example, the whole country or continent, there's something we need to consider, right? So the distortion on the map. So if we're talking about a large area, then the buffer with the distance is no longer a circle, right? It should be a ellipse. So in this case, if we're creating a 1,000 kilometer buffer, so the red ones are the Euclidean buffer or the planar buffer, and the blue ones are the geodesic buffer. You see how they look differently? Basically because the length measurement in the high latitude is different from the low latitude. And it becomes more extreme if we increase the width of the buffer. And this can create some very interesting misunderstanding. I found this graph from the magazine The Economist back in 2003. So they want to analyze the coverage of North Korea missile systems, short, mid, and long range. And they basically draw a buffer zone with the coverage of different systems. So do you think this makes sense? Or what's wrong with it? Well, apparently American people won't be too concerned because the longest range will only cover part of Alaska, right? So they should be relieved. But in fact, this is the updated graph The Economist published 2 weeks later in the next issue. So they correct their drawing. Well, now it seems a big threat to America, which is the actual case, the real case. So see if we get the buffer wrong in these circumstances, or how big the misunderstanding would be. All right, so that's a very short lecture section about the lens area measurement and the buffering of GIS. So now you will have a few tasks to practice how we create the geometric measurement and how to create a buffer along different feature data. All right, guys. Now I need to finish the last part of the lecture, which is related to the last 2 tasks in today's tutorial. So if you can take a break from the work you're doing, and let's look at the slides. So, I mean, I personally think this is the most interesting part so far about GIS. So we have talked a lot about processing the data, assigning the right coordinate system, and then measuring the distance, for example. But here, I think this part is really interesting because we're able to get some real results. For example, the least cost path from the data input. So here we're going to talk about the distance surface. So this is the process to create a surface representing the distance to travel from a location to the source location. So in the measurement tool, distance measurement or the buffering, we can specify a buffer zone or measure distance between 2 features. But what if we are interested in how to get to one feature from any location in this area? So now we need to use the distance surface tool to create a distance surface map that represents from any location what's the distance from that location to the source feature. So in this case, The source feature here is a line feature. So the input, the source feature can be raster or vector. Can be both raster and vector, but the surface, distance surface we're producing is a raster data. So in this case, our input is a road network represented by line features. And we're concerned about how to get to these road network from any given location on the map. So the distance surface is the raster data showing the distance from anywhere on the map to the source location. So this is the distance surface. So you can see it consists of concentric rings, represents the distance traveled to these features. So it's similar, looks similar to a contour map, but instead of representing the elevation, now we're representing the distance. So this is the physical distance or the Euclidean distance. But in many analyses we're trying to do, we're not only concerned about the absolute distance, we want to include the cost that we need to spend travel through these locations. So this cost here can be very abstract. It can be the time you consume to walk through the location, or the energy if you're going up a slope. Comparing going up the slope and going down slope, you're using different level of energy. So in that case, we're calculating a cost distance. So the cost distance is measured as a function of the physical distance and the cost. So of course, we still have the input of the feature. So same here is the road network. But now we have another input, which is in a raster model, showing in each location on this map what is the cost to travel. And this depends on, in this particular case, depends on the grade of the slope. So this raster data is color-coded, but in fact, each cell on this raster data has a value, I don't remember the range, but let's say from 1 to 5, showing different levels of slope grades. And we use this as the cost raster, the cost input. So by combining these two data sets, the raster and vector, we can calculate a distance surface raster. So see, this looks different from the physical distance raster, right? Because now we're considering the cost to travel through different locations on this map. And each single location has its own cost to travel through. The GIS program uses an algorithm called spreading algorithm to calculate the cost distance. So we have two inputs, the source raster or vector, which indicates the source locations, and the cost raster basically is this raster in blue, in different level of blue here. So the cost raster on each cell has a value representing the cost to travel through that cell. Okay? And if we look at the first step, we assign 0 to the source cell. And then the cell to the right of it is 1.5. And that is calculated using this equation here. So this value here is the accumulated cost. So this value is calculated based on the cost of these two locations, these two cells, and divided by 2. Because we're always traveling from the center from one cell to the center of the other cell. So similarly, we can calculate the least cumulative value or cost for this cell here. And that is 1 plus 3 divided by 2. And for diagonal, remember when we measure the diagonal distance in raster data, we use the square root 2 as the distance. So here we're using square root 2 multiplied by the sum of these two data divided by 2. So now these the values on these 3 cells represents the least cumulative value or cost travel from the source location to these 3 cells. So we can repeat the calculation for the rest of these cells. And for the next round, for each round of calculation, we always pick the cell with the lowest value. So that will make sure the accumulated value for the other cells, the new cells, are the lowest ones. Okay? So if we repeat this process for all the cells, we can get a cost distance surface. So now on each of the cell, we have a value that incorporate the cost distance, the cost for each cell itself, and also include the source feature, which is these 2 points. So imagine if we have a different source feature, if the source cell is in another location, we'll end up with a different cost surface. Okay, so in this case, we only have a 4x4 cell. And imagine once we have this cost distance surface, what we can do with it. So we know which cells has a lower cost. So when we travel through them, we will spend the lowest cost, right? So using this, we can calculate the least cost path. Let's look at this slide first. So the lowest path, the least cost path analysis is very important when we want to find the best route to transport people or resources from one location to another. And here we're considering the cost in terms of energy consumed or the cost you need to pay in this analysis. So using the cost distance surface tool, we can calculate a raster showing the cost distance. And this raster will provide us the basics to determine the least cost path from a destination to a source location. And tells us the least cumulative cost of getting from each cell to the nearest source. However, it doesn't tell us how we can get there, right? The value is for each cell, but how do we trace the least cost cells to get back to the source? So in the cost distance surface function, it also produces a direction raster or backlink raster. So this raster shows you what's the direction from this cell to its adjacent cells, which has the lowest cost. And this direction is coded by numbers and colors in ArcGIS. So if we're moving to the right, then the code is 1, and we use yellow to represent the direction. So let's say now we have a very simple cost distance raster here. And on this raster, we have this lower left corner as the source. So if we travel from the cell on the upper right, which has a 10.5 cost value, then the best way or the least cost path around it with these 3 cells is a cell with a cost value of 5.7. So you don't want to go to the cell with 7.5 and 6.4 because they will give you a higher cost. So you will follow this direction to your destination. And now in the direction raster or the backlink raster, this raster will have the same number of grid representing the same locations But instead of the cost value, it has the direction value from 0 to 8, showing which cell you should go next. Okay, and the next cell is the cell with the lowest accumulated value or cost. So let's look at a data set. So if we have a cost distance raster like this, so this is a destination, right? And each of these rings represents the cost traveled to the source. And this is how what the direction raster of this same cost surface looks like. So you see the color here follows a pattern, right? So if you're standing on like this location, basically the color tells you, okay, you should travel to the lower right, the lower left, in order to get to the source location. So this is the direction raster. In order to calculate the least cost path, you will need both the distance raster, the cost distance raster, and the direction raster. So in the task, you'll be producing both of them and use them to calculate the least cost path. And later, when you work with your own data set, if you zoom in really close to the raster direction raster, you will see how the calculated least cost path follows the direction raster. So basically, the direction raster, the color code, will tell which direction or which is the next cell the least cost path should go to. Okay, I think you'll get more better understanding when you are doing the task. So we'll be working with the same data set. And firstly, you'll be calculating the physical distance and then the cost distance. And based on these two, you're not using the road network as the source, but you're using a point feature which represents the outlook location, and then a set of point features representing different villages. So we're trying to find the shortest path or the least cost path from the outlook to each of these villages. Okay? All right, so let's get onto it.